Today we are going to learn about mastering regularization techniques in machine learning. We will explore how to prevent overfitting using L1 and L2 regularization techniques, implement them in Python, and interpret the results effectively. By the end, you'll be equipped with the skills to apply these techniques in your projects. Welcome to today's session on mastering regularization techniques in machine learning. Overfitting occurs when a model learns the training data too well, capturing noise and details that do not generalize to new data. This results in a model that performs well on training data but poorly on unseen data. Regularization is a technique used to prevent overfitting by introducing a penalty for complexity in the model. By the end of this video, you will understand how to implement L1 and L2 regularization in your projects, allowing your models to generalize better across different datasets. Overfitting is a common challenge in machine learning, where a model becomes too complex and captures the noise along with the underlying pattern of the data. Imagine a student who memorizes answers for a test rather than understanding the concepts. They may score well on the test but struggle with new questions. Similarly, an overfitted model performs exceptionally well on training data but fails to predict accurately on new, unseen data. Key indicators of overfitting include a large gap between training and validation error, and high variance in model predictions. To build models that perform well in real-world applications, it is crucial to ensure they generalize well, capturing only the true patterns in the data without the noise.
Regularization is a set of techniques used to prevent overfitting by adding a penalty for larger coefficients in the model. It essentially discourages complexity by adding a constraint to the model's optimization process. The two primary types of regularization used in machine learning are L1 and L2 regularization. L1 regularization, also known as Lasso, adds an absolute value of magnitude as a penalty term to the loss function, leading to sparse solutions. L2 regularization, or Ridge, adds a squared magnitude as the penalty, often resulting in smaller, more evenly distributed coefficients. By applying regularization, you can control the trade-off between bias and variance, ensuring your model remains robust and less sensitive to fluctuations in the training data.
L1 regularization, or Lasso, stands for least absolute shrinkage and selection operator. It adds a penalty equal to the absolute value of the coefficient's magnitude to the loss function. This penalty can shrink some coefficients to zero, effectively performing feature selection and leading to sparse solutions. Lasso is particularly useful when dealing with high-dimensional data where we suspect that only a few features are actually predictive. By driving less important feature coefficients to zero, Lasso simplifies the model, making it more interpretable. However, one limitation is that when features are highly correlated, Lasso may arbitrarily choose one and ignore others, which might not be ideal depending on the context.
L2 regularization, commonly known as Ridge, introduces a penalty equal to the square of the magnitude of coefficients to the loss function. Rather than driving coefficients to zero, it shrinks them, which is particularly useful when dealing with multicollinearity situation where predictor variables are highly correlated. Ridge regularization helps in distributing the coefficient weight more evenly among correlated features, thus maintaining stability in predictions. It's beneficial for datasets with many features, as it helps in reducing model variance without eliminating features. However, unlike Lasso, Ridge does not inherently perform feature selection, meaning all features will remain part of the model, potentially complicating interpretability.
Choosing between L1 and L2 regularization involves understanding their impacts on the dataset and the problem at hand. If your primary goal is feature selection or if you expect that only a small subset of features is relevant, L1 regularization is a suitable choice due to its ability to produce sparse solutions. On the other hand, if your dataset has multicollinearity issues or if all features are expected to contribute, L2 regularization is more appropriate as it shrinks coefficients but does not eliminate them. In practice, often a combination of both, known as elastic net, is employed to leverage the benefits of both methods. It's crucial to experiment with both techniques to see which one yields better validation performance for your specific use case.
Implementing regularization techniques in Python is straightforward using libraries like scikit-learn. To start, ensure you have scikit-learn installed. For L1 regularization, you can use the Lasso class, and for L2 regularization, the Ridge class. Here's a quick example. Import the required classes and split your data into training and testing sets. Fit the model using Lasso or Ridge with your dataset. Evaluate the model performance using metrics like mean squared error or R-squared to see the impact of regularization. Additionally, scikit-learn allows you to adjust the regularization strength using the alpha parameter, enabling you to fine-tune the balance between bias and variance. By following these steps, you can easily incorporate regularization into your machine learning pipeline.
After implementing regularization, interpreting the results is crucial for understanding its impact on your model. Begin by examining the coefficient values. L1 regularization may result in zero coefficients for some features, indicating feature exclusion, while L2 regularization will show smaller, more balanced coefficients. Evaluate the model's performance on validation data to check improvements in generalization. Regularization often increases bias slightly but reduces variance significantly, leading to better performance on unseen data. Visualizing the model's predictions versus actual values can provide insights into how well the model generalizes. Adjust the alpha parameter to find the optimal regularization strength that minimizes validation error, ensuring the right balance between underfitting and overfitting. While regularization is a powerful tool, there are common pitfalls to be aware of. One major mistake is ignoring the characteristics of your dataset, such as multicollinearity or the presence of irrelevant features, which should guide your choice between L1 and L2. Over-regularization can also occur, where too much penalty leads to underfitting, so it's important to experiment with different alpha values. Misinterpreting results, such as assuming a feature with a zero coefficient in Lasso isn't important, can lead to incorrect conclusions. Always perform cross-validation to ensure your model's performance is consistent across different subsets of data. Lastly, remember to scale your features, as regularization is sensitive to the scale of data, impacting the weighting of different features.
Regularization techniques have significant real-world applications across various domains. In finance and economics, they help in building robust predictive models for stock prices or economic indicators by handling large datasets with many variables. In healthcare, regularization assists in creating diagnostic models that generalize well from training data to unseen patient data, making them reliable for clinical use. Marketing models benefit from regularization by identifying the most impactful features that drive customer behavior, optimizing marketing strategies. In the field of image recognition, regularization helps in dealing with high-dimensional data, improving model accuracy and performance. Lastly, in natural language processing, regularization is crucial in handling the vast amount of features generated from text data, ensuring models remain efficient and effective. In conclusion, mastering regularization techniques is essential for building machine learning models that perform well in real-world scenarios. By understanding and implementing L1 and L2 regularization, you can effectively prevent overfitting and improve model generalization. We encourage you to experiment with these techniques in your own projects, adjusting parameters and evaluating performance to find the optimal configuration. For those interested in delving deeper, numerous resources and courses are available online to expand your knowledge. Thank you for joining us today, and we wish you the best in your machine learning endeavors.